All right, can everybody hear me? Good. So, my name's Zach Borton. I'm currently working at Rivian, who is about to release an electric truck and electric SUV. Before that, I used to work at a wind tunnel. So, the long story short is I have lots of aerodynamic testing experience. Um, for my master's degree, I did in automotive systems, and then a lot of my undergrad stuff in my senior design was on vehicle kinematics and dynamics. So I have the whole automotive systems minus powertrain pretty well covered. So with all of these slides going forward, I've really tried to condense it down. So if you have any questions, just wait till the end and I can probably go back and answer a whole bunch more on it. And as a side note, I can't tell you what vehicles I've worked on, but approximately half of them in the presentation I have. So I'll let you guess which ones those are. All right, so you decided to build a race car. How do you decide what to do? How do you make it go faster? So the obvious choice is really good tires. Another good option, lower weight. That's going to reduce your rolling resistance. Next, we can go with vehicle setup, and that's going to be suspension setup, springs, dampers, chassis stiffness, all of those type of parameters. Aerodynamics, which I'll cover in probably more detail than anything else. And then I'm not really going to cover power train at all, mainly due to number one, it's one of the least important things with this. And then also we're in this very large change of everybody's changing what powertrain they're using, whether it's gasoline, diesel, hybrid, electric, hydrogen powered. It's all coming into play, and each one of those deserve a whole presentation in and of themselves. So on that note, tires. Tires are the only thing that actually touch the road. So it's very important that we understand what's going on with them and that we get them the best contact patch that we can. So some things that a lot of people don't realize about tires are if a tire is not slipping, it has no grip. Now, I'm not saying that you need to be doing burnouts, but more of if there is no slip, there is no grip. You can definitely see that in this lower one right here. No slip ratio, you have no friction. So we kind of break this up into slip ratio and slip angle. Slip ratio is when you're braking and accelerating, and then slip angle is with cornering. So as you slip, you somewhat linearly increase up until your max target, and then you really drop off. And that's kind of like you're going around a corner and your tires start squealing and then all of a sudden you start sliding off the road. Doesn't mean you lose friction, it just means that it's significantly decreased, and we're all pretty much used to that. The more interesting thing is tire friction is nonlinear. So as you add load to your tire, your friction force is going to go down. So that's why just adding bags of sand to the back of your vehicle isn't that helpful going around a corner. It may change the center of gravity for your vehicle that helps you out, but it doesn't actually help you go around a corner. So that'll become very important as we talk about some of the stuff coming up. Weight reduction. The easiest thing to do here is to just not have that part on the car. If you're building a race car, you don't spend the time to have air conditioning. You don't spend the time to have really nice automatic windows kind of thing. So not putting it in the car, that's your weight reduction, and weight reduction reduces your rolling resistance and it reduces your inertia. So one of the main things that we can do is use materials in the best way possible. So it really goes into selection of what that material is, but also where those materials are used. The next one is where can you add holes or essentially just remove that material from. And like I said earlier, just get rid of all the unused parts that you're not using. If it's a race car, it's not about occupant comfort, it's about going fast. So material selection. You can kind of see here in the top chart, all the materials, for the most part, have a very useful impact in their strength, but also in their density. And so when you're designing parts, you got to kind of keep that in mind. Okay, steel, really, really strong, pretty dense. Aluminum is about a third of that for density, but also for strength. So your specific strength is about the same between them. So you need to kind of figure out when are you going to use one material over another material. And that kind of comes into, if I'm building just a beam or a floor or a panel, if I make it out of aluminum, I can make it twice as thick as a steel one, have it be slightly less overall mass for it, but still have it be stronger overall in bending kind of thing, just because of the lower density. So even though it's less strength, you're able to increase its strength and decrease its mass overall. Another good thing to think about with this is temperature and vibration. These are typically the two things that people forget about most when designing stuff. It's really easy to say, okay, this member has to take 500 kilograms of force, but they forget that, oh, it's 500 kilograms of force when it's at 200 degrees C, and it's not just static, it's going to be vibrating the whole time. And so you need to keep all of those loading conditions in your mind as you're designing these things. So that's where, like, titanium's great, your nickel alloys are great for high heat, but do you necessarily need them if you're really, really low temperature? Probably not, and you can go with a less dense material kind of thing. For adding holes, the main thing that we'll use to analyze a part is called finite element analysis. Essentially, you're breaking the part up into thousands of little elements. You're running stresses on them. Simple stuff you can do by hand. Once you get into a lot more complicated, doing it computationally is advantageous. And then, as you can kind of see in the bottom right, red is high stress, blue is low stress. So, okay, this corner probably isn't needed. Let's redesign it. We'll remove this blue area, rerun it. And essentially what we try and do is get the entire part having the same stress that's just below its limit, and then do that for every single type of loading case and make sure that no material is on there unless it's actually adding strength to the part. So chassis setup. This is going to be your springs, your dampers, your control arm geometry, and your actual chassis. So key parameters, wheelbase, this is the front axle to rear axle width, and then track width is your left tires, your right tires. And why is that important? Because we need to make sure that we understand and know where our center of gravity is, and then how our center of gravity is going to impact the tires as we're going around corners. So if we're really, really long vehicle, then as we move around, it's going to change less on our front axle and a rear axle versus a really short vehicle. Conversely, that makes it a lot harder to be able to turn, kind of thing. For vehicle dynamics, we can change springs. That's going to change both your pitch, your pitching moment. It's going to change your rolling moment. And then we can add in dampers on that. So not only are we adding in your spring stiffness, but you're adding in your dampers, which are effective at removing energy at velocities instead of just displacements like springs are. And then you get into other similar items like anti-roll bar, where you're coupling your right side and your left side. Third springs or heave springs, you're kind of coupling the front and rear essentially, where if you're going, heave is up with the vehicle, so that basically will stop the vehicle from going up, and then it also helps it for when it goes down. Aerodynamics. This is kind of my love and what I've been doing for the last decade or so. So I'm going to show you the Navier-Stokes equation. This is the physics that explains the fluid flow. It takes into account the mass, the viscosity, the acceleration, everything else. And it's crazy complicated. And I'm not going to drive it for you because it would take a couple hours. But essentially, once you have all those things, we can split it up into the X, Y, and Z components along with continuity. You can also add in some of your thermal equations and then be able to do thermal analysis as well. But these equations, typically we don't actually solve them just in general, but what we will do is we will computationally solve these for around a vehicle or for an HVAC unit or anything like that. So kind of stepping back from there a little bit, we have the ideal gas law, PV equals nRT. Sure, a lot of you have seen that. And that comes into play with just general understanding of how your fluids are going to move about. And then we have Boyle's law where P1V1 is equal to P2V2. And that kind of goes into the next part of Bernoulli's principle and the Venturi effect. So essentially, as we speed a fluid up, it decreases in pressure. So as it goes around a vehicle or around a wing, it's going to drop in pressure. And at some point, you'll get separation, or you get some other issues with dropping in pressure. Or if you really slow the velocity down, then you're going to increase your pressure. So we need to think about how we can take advantage of this. And for race cars, what we're trying to do essentially is add a lot of high pressure air on top of our car, and we're trying to add a lot of low pressure air below our car. So that way you have high pressure on top, low pressure on bottom, and effectively you're pushing your car down. So one of the questions that's going to come up is, should you be looking at compressible flow or incompressible flow? So typically all liquids, water, gasoline, all that, we consider incompressible, because if you try and push on it, you can't change its volume, hence going back to PV equals nRT. But air, you can push on it hard enough that you can get a displacement. However, if you actually run the calculations, you find that below about 1/3 of a Mach number, you end up essentially not needing to worry about compressible flow. So that's going to be all of your normal production consumer cars, and that's going to be pretty much all of your race cars, except for drag racing, which gets up to 300. Although I can definitely tell you they do not look at compressible flow, just because of the increased costs with testing of it, because then you start getting into essentially shock waves, and then you have heat transfer issues, and your model needs to be all stainless steel, is the long story short. So as the air is coming towards your vehicle, you will build up a boundary layer on the bottom. So in your free stream, it's just standard. Your velocity at the top is equal to your velocity at the bottom. And then as you start accelerating or maintaining flow along the vehicle, your bottom, since it's actually touching the vehicle, has to be 0, but you still have your free stream flow that's at free stream flow. And so there's this region kind of in between the two, and that's what we call the boundary layer. And that's essentially this curve of this speed up. And so your boundary layer grows as you continue along the vehicle. And you have essentially a laminar boundary layer, and then eventually it trips itself, and then you get into a turbulent boundary layer. Once you get into turbulent boundary layer, your curve is a lot less of a curve, and it's a lot flatter and then comes up. So this is one of the things that we worry a lot about, of where are we tripping these things at between laminar and turbulent, and how can we deal with them? So as I just mentioned, we have laminar flow and we have turbulent flow. And if we are laminar, we're below a Reynolds number of 2300, which is pretty low, as you can see by my little suggestions right here. of a vehicle going about 16 miles an hour will only be laminar for about the first 5 millimeters or so. So that is pretty darn slow. And where I'm going with this is there's a large myth that you want to try and keep the flow across the vehicle laminar. And that's just not the case. You can't physically do it without some very specific techniques. So the point being, everywhere is laminar, just at the very, very front. And so we don't really consider that. We just assume everywhere is turbulent for the entire vehicle. But we do try and focus on is where the flow ends up separating at. Oh. All right, so I just mentioned Reynolds numbers. I'm guessing a lot of you don't know what that is. And essentially, the Reynolds number is trying to explain what the fluid is like at a certain size and a certain velocity. And that comes down to the inertial forces in the fluids and the viscous fluid forces. So how do we actually use this and where is it relevant? Like I just mentioned earlier, it's for trying to determine when you're at laminar flow or turbulent flow, but also if we're trying to do scale model testing, right? Just because we don't want to put in the entire large vehicle, we want to do a much smaller one. Okay, well, since we have this relationship of velocity and length, if we're at half the length, then essentially we need to go twice as fast to maintain our Reynolds number. Hence how we can do scale model testing. Except there's this large issue of Reynolds sensitivity. So as you change your Reynolds number, especially for airfoils, flat plates, even for like ellipses and spheres or circles or rods, you get this relationship where your drag force, or it can be lift as well, is continuing to change depending on what your Reynolds number. So one of the things that we do whenever we're starting a test, whether it's full scale or model scale, is we always do a Reynolds sensitivity study where we take the vehicle and we go low speed and we slowly increase its velocity up. And then we try and understand when we stop changing our drag force at. So we go up, we're at 40 meters per second, we go to 50 meters per second and it changed. We then go to 60 meters per second. Now it's the same as it was at 50 meters a second. So now we know that we're not Reynolds sensitive anymore. And that's mainly because vehicles are a lot closer to flat plates than they are to airfoils. So vehicle drag. There's two ways to look at this. Essentially, you can use the first equation and get what your actual coefficient of drag is. And I'll explain what the coefficient of drag is. And it's essentially the shape effect of your vehicle. So you have the forces being applied to it, you know what your fluid is, you know the frontal area of your vehicle, and then we get this shape of what the whole vehicle is, and it's unitless, hence it being a coefficient. And so that's what the vehicle manufacturers will publish, is what their CD is. Like the Tesla Model S just came out with the 208 CDA, which is really quite low. Or you can look at it the other way of, you already know what that coefficient is because you measured it at a wind tunnel, and you know what the frontal area is because you have it in CAD. And so you can say, okay, I want the vehicle, or I want to know what the aerodynamic force is on the vehicle when it's at highway speed. Then you can use the second force, and then this equation will get used in our vehicle models. So that way we can calculate out for that lap sim that I was talking about at the beginning. Okay, if my CD is this and my frontal area is this, I know what the force is, and I can kind of tell how long it's going to take to go around a lap. So why is drag bad? Essentially, everywhere around the race course, especially as you get faster, you're adding additional force that's trying to stop you from going forward. So it's slowing you down, which means that you're not going to pass as many cars, but also you're needing more power to maintain a certain speed. And so you're using more fuel, whether that's electricity, gas, diesel, whatever, you're using more fuel or energy to be able to do it. And to compound that even more, your drag power is actually to the third instead of just to the squared. So you're using significantly more power as you increase in speed. And then why is downforce so useful? Essentially, downforce is giving you that force that is down to add to the normal force of your tires, except you don't have any inertia. So normally, instead of just adding in like 100 kilogram force into your vehicle, that's great for getting the normal force increase in the friction with the tires, but you then have to accelerate it, you then have to decelerate it, you then have to deal with it going around a corner kind of thing. Or if it's downforce, that isn't, you have no inertia. There is no mass there. All there is a singular force over the vehicle pushing down onto it. So how do we actually measure these? We can do full scale testing where we take a production car or your actual race car. You can go to the wind tunnel. You can do scale testing where you essentially build a model of that, whether it's 8 scale, half scale, whatever. You can do computational fluid dynamics, which, as I kind of talked about with the Navier-Stokes equations, you essentially solve those and then you end up with the flow around a vehicle. And then the last option is coast down testing. So you go out into an asphalt lake. You can actually do this on the road, except not really legally because you're probably going too fast and then you're impeding traffic as you slow down. But this is how EPA actually certifies a vehicle for its mile per gallon range, just as an FYI. So the first thing that you can do, a lot of people consider this the gold standard, is full-scale wind tunnel testing. We have one of these in the country right now. It's in North Carolina. That's large enough for a full vehicle and has a rolling road. And essentially, you can put in an actual vehicle. As you can see up top, you have the Corvette DP car, and that you can put in the actual car with actual race parts, with an actual engine, and therefore, in theory, get the most accurate numbers. Your second option is scale model testing. One of the main reasons that you use scale model over full scale is due to cost. And then also it allows you to be able to change parts out easier, faster, quicker. And then one of the more interesting things you can do is use like a PIV capture system where you're essentially adding small little bubbles into the air using lasers to scan where those bubbles are. Typically those only have about 500 millimeter by 500 millimeter scan that you can take a look at. So if it's a smaller vehicle, then essentially you're able to capture a larger part of the rear or front or side of it. Whereas on a full-scale vehicle, it's very small and it's really only useful around mirrors and whatnot else. The next thing we can take a look at is computational fluid dynamics. Like I said, you're essentially solving the Navier-Stokes equation, and there's a whole bunch of models for turbulence models. RANS is pretty common for steady state stuff like HVAC. If you're wanting to use like an actual vehicle, industry standard is now at LES, Large Eddy Simulation. To help kind of explain what happens here is you take your CAD, you create an STL file of it where it's tiny little triangle meshes. You then put it into a large volume, and then you remove all of the vehicle essentially. And so you have this large mesh around your car. That's going to be your air or fluid. As you're closer to the vehicle, you can kind of see these, your squares get smaller. And as you get further away, you can use bigger squares just due to the changes in the air velocity and pressure aren't as large as you get further away from the vehicle. Use Navier-Stokes to essentially solve all those equations. I can tell you we use about 1,000 cores, and it takes us about 12 to 24 hours to solve this. So significant amount of computational processing is needed for all this to happen. The great thing about CFD though is you get so much information. You get pressures everywhere, not just on the body, not just where you have a rake at, but everywhere around the vehicle, 10 feet above the vehicle. You can know what your pressure is there. You can know what the free stream velocity is there. And so it gives you a lot better understanding of the vehicle than just in the wind tunnel. The next thing you can do is coast down testing. The SAE standard is you bring it up to 70 miles an hour and throw the car into neutral, let it coast down, as the name implies, to 10 miles an hour. And then you'll essentially get some plots that look like on the right. And then we can extrapolate out from there your aerodynamic forces. So kind of with this plot, you can see you have your total in purple, your green is aero, B is your rolling resistance. A lot of that is due to weight, hence what we were talking about earlier of trying to remove mass. And then you have a static drag as well. So you want to design a race car, production car, or whatnot. How do we actually go about reducing drag? The simple answer is look at this vehicle and you should have a pretty good idea. Very large radius on the front, especially coming around towards the tires. That'll help out a lot. Hard trailing edges. And these two things combine together to make it really hard for designers to come up with a design that looks nice of where it's large and swoopy at the front and hard edges at the rear. If you're working on race cars, you don't have to worry about that at all. Covering the tires, anywhere from about 20 to 50% of your drag is going to come from tires, hence why covering them up is very, very useful. That can be from an actual cover, like is on the rear of this vehicle, to the front of just closing in your spokes as much as possible. You still want to be able to have your brakes be able to cool down, but you want to close that off as much as possible. And also just using like a thicker, wider, non-low profile tire will help with that as well. All right, so how do we increase downforce? Essentially, like I said earlier, high pressure on top, low pressure on bottom. That's going to help you out a lot. Wings are very efficient generators of downforce, so that is very useful. That mainly gets used on the rear. On open wheel cars, it'll get used on the front. You can use a diffuser, which is essentially the bottom side of a wing you can put on your car, where you are diffusing the air out by expanding it. And at the front of your diffuser, you're significantly increasing its velocity, hence reducing its pressure, hence getting that low pressure on the underside. At the front, you can run a splitter. This is kind of a hammer approach, but essentially you have something stick out. And since you have something right behind it, it accumulates the air, gets higher pressure, it extends out in front, you get the higher pressure on top of your splitter, that's adding some downforce. And then you can essentially do the same thing at the rear, where air is coming over, it's hitting your spoiler, it's building up pressure there, and then you have the body just in front of that, that's also seeing that high pressure, and that's pushing it down as well. All right, so I know I covered a ton of stuff and not nearly as much detail as I would like. What questions does everybody have?
I have two questions. One, what would you say is the difference between designing an electric pickup truck and designing like a regular electric car? And two, what software do you use for computational fluid dynamics testing?
All right, so I'll answer your second question first. What programs do we use? Where I'm currently working for external aerodynamics, we use a program called Elements. It's based on the open source OpenFOAM. You can go online, it's free. It's honestly one of the best solvers out there. I can tell you GM is working on their own version of OpenFOAM. A couple other startups I know are using a different version of OpenFOAM. There's also StarCCM that you can use, and there's a few others out there. And then on to your first question of what's the difference between designing an electric pickup or vehicle and just a standard one. It really is twofold. The first is you don't have an engine or exhaust, which skipping over that, it's mainly the exhaust system. It's really hot, it's underneath, and it's really hard to put underfloor shields, essentially panels underneath, due to the high heat. And so when you don't have that, you're able to put those shields underneath, and that really helps reduce drag. And then the other thing is with batteries being so expensive, it's a lot more advantageous to spend additional money on aerodynamics to get a lower drag vehicle. So yes, you probably could get to the same drag numbers with an ICE vehicle versus an electric vehicle, but nobody's going to want to spend that extra money on the normal vehicle versus an electric vehicle.
Why is that?
Because batteries are so expensive. I mean, that's what it really comes down to. Like half or so of the car is like cost of the car is the battery, right? Where that is not, that's not it with a normal combustion car. That's only like 10% or so of your vehicle cost. So that's why you're seeing cars like Tesla, they're trying to stay upmarket kind of thing. So that way they can help justify that additional cost. Hence why Audi has an electric vehicle and Porsche has an electric vehicle, but it's taken a little while for Volkswagen to finally get their electric vehicle out. Any other questions?
I do have a question. I don't remember correctly which one was the most efficient as the test for the vehicle, but if I'm not mistaken, was the CFD, like is the CFD the less efficient method, or the one that is less accurate?
CFD is one of those, just like tunnel testing or any other type of testing, it's all in the setup. If you set everything up correctly, your solvers at this point are pretty darn good, and you're going to get pretty decent results out. Anywhere you test, any program you test, or every program you test, like I said, we use OpenFOAM, use StarCCM, use Elements. They're all going to give you different answers. You go to this wind tunnel, that wind tunnel, the next wind tunnel, they're all going to give you different answers. They're all going to be pretty close, but they're all going to give you different answers. And it's kind of like the best way I can think to explain it is if I hand you this part and I ask you to measure how tall it is, and then I ask the next person, and then I ask the next person, then I ask the next person, they're all going to be really close to the same number, but everybody's going to give me a different answer because one person's going to use a ruler, one person's going to use a caliper, one person's going to use a caliper but hold it slightly different. So are any of them more accurate than another one? It really depends. CFD has the tendency, if you don't set it up correctly, which is reasonably common, to have issues. I can tell you the full-scale tunnel that we go to we're investigating it for how they're doing their tears, right? And so a tear is, if you're trying to measure downforce, you put the car on the scale, and then you remove the weight of the car, and then you spin it up, blow the wind on it, and then you see how much downforce it is by subtracting out the weight of the car. It's way, way more complicated than that, but essentially they do it differently than some other places. And so we're kind of starting to question, is that the correct way to do it, or should we start developing our own way to do it, kind of thing. And so the answer is none of them are perfect. All of them have issues. And the main thing is, at least for production cars, is coast down is what the EPA accepts. But what numbers do we actually publish? It depends. What numbers do we actually track in our logs? It kind of depends. We don't use any single source for our numbers. I'll put it that way. Any other questions?
I have a quick question. So with scaled down models, like, is there some inaccuracy that comes from like just having the same air, but different sizes for things?
Yes, so that's a good question. And I attempted to explain it with the Reynolds number. So yeah, if you take a look, and ideally what you try and do when you scale the model down, hence the L, is when you change your L to half or quarter of what it is, to compensate for that, you change your velocity. That's your little U right there. So as one goes down, the other one comes up, and we try and maintain a Reynolds number that's similar. So for that, like production cars, it's reasonably easy. You can find scale tunnels that'll do 50 to 60 meters per second, which is 112 to like 125 miles per hour. And so when you take half of that, that gets you like 60-ish miles per hour, which is going down a normal road kind of thing. And so that puts you in the ballpark. So that's ideally what you want to do. If you're looking more at race cars where they're going 200 or so mile an hour down the straight, that's just not going to be possible. Not only are you not getting that speed all the way up to what the actual vehicle's doing, but then you're also not compensating for being at scale. So that's why we really look into this Reynolds sensitivity. So like I was saying, what we do is we put your scale vehicle in, we test it at 10 meters a second, 20, 30, 40, 50, 60, whatever the tunnel goes up to. And you can kind of see the coefficient of drag. It usually comes down, and then it stabilizes out at a certain rate, or hopefully it does. If it doesn't, if it keeps coming down kind of thing, then you haven't hit Reynolds sensitivity, and I can't test this vehicle at this scale at this tunnel, and then you have to essentially go to a different tunnel. And so if you get into like really, really aerodynamic vehicles, like the X Prize cars from about 10 years ago, those might have an issue working in the tunnel. If you're trying to do like a delivery van or a truck or something that's a pretty blunt object, those are a lot closer to flat plates, and then you're going to be Reynolds stable at like 30, 40, 50 meters a second. And then that you're good to be able to test there.
Gotcha. Thank you.
Yep.
I have a question. What do you spend most of your time doing, like on a day-to-day basis?
I spend way more time than I would like emailing and talking to people to try and make things happen to get to these tests. I really like doing the physical tests and getting to them. We just get to do like one every month or two. And so we put in a lot of work for getting ready for that. And it's essentially trying to get all the correct tires there, trying to get all the correct body panels there, especially when you don't because you're trying to design a car, and so you don't have all of the production parts ready, right? So you have to like rapid prototype parts, which is a lot easier when it's at scale than it is at full scale kind of thing. So trying to wrangle people to get me parts, that's way more of a something that I do. And then actually designing this kind of stuff, it's going in, CADing up a wind tunnel model, whether it's full scale or model scale. And then if I'm doing CFD, then it's setting up a CFD model. So typically what we'll do is every so often we'll rebuild the entire model from the ground up. And then as things go on and things change, we'll just add those changes into the vehicle. And so it's a lot of time going into, it's like CAD, but it's a surfacing software where we can take and essentially deal with the surfaces. That surfacing software also has meshing capabilities where we can mesh it, like I was kind of talking about earlier. You create a whole bunch of little triangles. It's like 20, 30, 40, 50 million triangles that you create for the body and frame and chassis and suspension and everything, like absolutely everything that touches the air. You then export it out. Running the CFD, it takes you like 30 minutes to set up a run, takes 24 to 48 hours to actually get the results back. And then you spend maybe a couple hours taking a look at the results. The results you get out of it, you're gonna get slices of pressure, slices of velocity. For the most part, we don't actually use the streamlines that everybody sees. Yeah, and then you try and take a look at those, get a really good understanding for why is the vehicle drag or downforce what it is. And then thinking about it, what can I do to improve that kind of thing? And so that's where CFD comes in really handy, is it gives you so much of a better understanding around the vehicle of where you can attack. Okay, it's clearly this mirror, just the bottom side, I need to really focus on kind of thing. So yeah, that's essentially what my day is. And then every now and then I make a PowerPoint like this.
Okay, cool. Thank you.
Yep.
Real quick, guys, if anyone else has any questions, feel free. But I'm also going to post just a real quick Google form in the chat, just because we're starting to get some participants from other institutions. I'd like to just kind of keep track of where people are from and kind of, you know, what the involvement is. So if you wouldn't mind taking just 2 or 3 minutes to fill out this quick little form, I'd really appreciate it. And again, I'll leave the floor back open if anyone else has any questions.
I'm sorry, I disconnected like in the last couple of minutes. Did I miss something? I think the
Other than me just posting that quick little 2 or 3 minute survey, I don't think you missed much. We're just asking and answering questions right now.
okay, thank you.
Yeah.
I do have another question relating to the testing you usually do. So again, with the analogy of the measurement of how tall something is, right? As a company, right? Would you prefer to do several tests, different tests, or just invest in one test? And if you do invest in just one test, like, will you go to the most economic one, or like what is the position a company or as a group of people designing a race car will take when it comes to the correct test?
Okay, so I'm going to answer this personally and not part of my company, just so there's no questions there. If I had to do it, I would use essentially all 4 of them. All of them exist for a reason: coast down, CFD, full scale, model scale. They all have their pros and cons, and it's really when should I use one of them and when should I use the other one? So I'll kind of switch back a little bit. Early on, CFD is great. CFD is great because you can essentially set up a CFD model in about a week, highly detailed model in about a week. To do a scale model, it takes about 3 months or so to make. A full scale model is going to probably be in about the same amount of time, depending on how much detail you want to put in. And coast down testing, I wouldn't bother with that until you get like an actual vehicle. So CFD is great, like I said at the beginning, because it's so fast. You can get up, you can start getting some answers in it. And it's great in that it helps when you're making huge changes, right? Like, should I have the radiator exit out of the hood or through the wheel wells or down below, right? Like that's a great thing to do with CFD, because if you tried to do that with an actual car or with a model, you're cutting it up so much that it's really hard to do and you're wasting a lot of time. So kind of from there, I'd be looking at doing scale model testing. Scale model testing is about half the price of everything else. So economically, it's cheap, but also it's a lot faster. I can get in a run, and when I say a run, I mean like a wing setting, essentially in half the time that I can at full scale testing. But I can also get in that run in about 2.5 minutes. So that's great. And then scale model testing along with full scale testing, I can get the vehicle at different ride heights, different pitches. So ride height is you can go up, you can go down, you can pitch, so nose down or nose up. You can test where you tilt the model one way or the other. That's called yaw. And that we typically simulate for side wind forces. So you can do your vector analysis when you're at an angle. Okay, we're at 3 degrees, and we know that we're still at this at 100 meters per second. What is our effective side velocity kind of thing? And so we'll use that to be able to get the side wind cases to understand those. And all those, I can get each one of those for every part in 2.5 minutes, which is great. The scale model, like I was talking about a little bit earlier, I can change parts on that really quickly. Since it's not a real vehicle, a lot of times it's carbon fiber or prototype parts or whatnot else. And we design those to facilitate changing those parts on and off really fast. So that's also pretty great in the beginning. But like I said, it takes about 3 months or so to build that. And then as you're designing and building that, you're also designing and building your full scale. So one of the things that you can kind of see with this, typically model scale, you have a sting coming in, and that's what actually holds the vehicle in the wind tunnel is from above, right? And so anything really behind that sting is kind of questionable in how it's working. So for this, if you're trying to measure how much air is going in through this little hoop where you maybe have like your engine intake, it's probably not going to be as good a data as you want kind of thing. And even the rear wing, you might have a little bit of an issue with getting good data. And so when you're doing that, you might want to look into having wheel arms come out like these at the full scale testing. And so having this in full scale, we can get a lot better flow to the rear wing. But conversely, since we have these wheel arms here, we're not getting the flow along the side as accurately as what we would in scale model testing. And so you kind of switch between full scale and model scale. Like I said, you're spending twice as much or so to go to full scale testing. I can tell you, like I said, the only rolling road full scale wind tunnel in the US charges $4,000 an hour, which is $1.15 a second. So you are spending a ton of money trying to develop a car there. Is it a great place to do it? Yeah, but you have to have the money to bankroll it, and it's probably not going to be your best bet to just do all of your development there. And so that's why I come into the scale model. Like I said, you gain some abilities, and then you kind of switch between the two. In between the test, I would still be running some CFD runs as often as possible. And this is why we have whole teams that are dedicated to a vehicle to get it running and get it onto the racetrack or into production kind of thing. And then coast down testing, I wouldn't worry about that until you actually get a car in production or ready to race essentially. And then I'd use it for setup changes, like wing changes. Okay, this wing versus this wing versus this wing kind of thing. Or if it's a production car, you can kind of use it for evaluating the actual production parts. And then you can do some changes. But the main issue that comes with coast down testing is side wind is an issue. So how do you do a side wind? And it's not the same through every run, or even like during the run, it might blow all of a sudden. We do put anemometers on top of the roof that measure your wind velocity and then also angle, so we can kind of back calculate that out to help improve our accuracy, but it still kind of comes into question there. So that would be kind of one of those where I do last, and that's really getting into like specific changes on the car.
All right, well, guys, thank you so much for coming. I do know that Zach has a meeting in about 3 minutes, so I want to make sure that he's got time to transition over to that. But you know, on behalf of the Physics Honor Society, the Bothell chapter, and personally, Zach, also just want to say a big thank you. Really appreciate you taking the time to put together this presentation for us, and then of course share it with us and answer questions. So big round of applause for you. Thank you very much.